This is the electromagnetic tutorial presented by the S.A. Charles V.B. Hello, welcome to a new tutorial presented by the S.A. Charles V.B. In this tutorial, we're going to see electromagnetism. Now, electromagnetism is a process by which there is a production of electric current when a certain current carrying conductor, there is a production of electric current or an electric EMF when a certain conductor is moving with a certain force F in a B field. And this is exactly what happens in Edea, Cameroon. In Edea, Cameroon, you need to know that there is waterfall, and the waterfall which at the level of the Edea, Cameroon are going to cause the turbines to move. These turbines produce a force which causes the different coils to move inside a magnetic field, and that movement of the coils inside the different magnetic fields are going to produce an EMF, and this EMF is going to produce the current which can be transferred to the different parts of Cameroon. Now let's have some definition of terms which can be used in electromagnetism. Number one term that we're going to have is the Joule effect. The Joule effect, this refers to the ability of a conductor to dissipate heat once current flow through it. And the formula for the Joule effect is given as E is equals to the P is the power. The Joule effect is the power. So that power will be equals to EI, which is the current, squared times the resistance of the conductor which dissipate the heat. Now, the self-induction. What is self-induction? This refers to the ability of a material to induce itself with voltage once it cuts through magnetic field lines. So in this case, we are going to have a material which induces itself an EMF when it cut magnetic field lines produce, or magnetic field lines which is enhanced on it. We have again motor induction. Motor induction refers to the ability of one material to induce an EMF in another material once the latter, the other material, cuts through the magnetic field line produced by the former material. Now, let's see the laws of electromagnetism. The law of electromagnetics are divided into there are two main laws involved in electromagnetics. We have number one, we have the Faraday's law, and number two, the Lenz's law. The Faraday's law states that the EMF induced is directly proportional to the rate at which the magnetic fields, the magnetic flux linkage are being cut with respect to time, and this phi is representing the magnetic flux linkage. So the EMF is equals to Kd of phi all over dt, where K has experimentally been shown to be 1. So EMF is equals to d phi over dt. Now let's visualize the Lenz law. The Lenz law is only a modification, a slight modification of the Faraday's law, just by adding a negative sign here. So it's just saying that the EMF is going to be equal to negative d phi all over the dt as shown here. But this negative sign here has a very high implication when it is explained qualitatively. So what's the meaning of this negative sign here? It states that the Lenz law, via this negative sign, states that the direction of the current and the EMF induced will be in such a way to oppose the change producing it. So let's visualize the illustration of the Lenz law via this diagram. Let's say you have a magnet here with a north pole and a south pole, and we need to know that with the magnet, the magnetic field lines are moving away from the north pole and are coming into the south pole. This is similar with the charges, the positive and negative charges. The positive charges had electric field line moving away from the positive charges, and negative charges had electric field line moving into red. So now this is north pole and south pole. The north pole here let's say you are moving this magnet with the north pole here in this direction. As you are moving in this direction, we are going to produce a corresponding north pole here on this coil, on this solenoid, and we are going to produce a corresponding south pole here by Lenz's law. So Lenz's law just states that a north pole is going to be produced here in order to oppose the movement of the change producing it, and that change is due to the direction of motion of this magnet into this solenoid. So this current is going to, the direction of current is going to be in such a way that the north pole should be produced here and the south pole should be produced here in order to prevent further movement of the magnet into the solenoid. So you are going to use now the right hand grip rule in order for you to visualize the direction of current. So the direction of current via the right hand grip rule. So when you are going to use the right hand grip rule, you visualize that the current is going to move here for you to have a north pole here and a south pole here. The right hand grip rule, you can just imagine that you are holding a screw. You have the thumb of the screw will be the direction perpendicular to the cock in which the cock of which you are screwing, and the direction of the screw is going to be the direction of the other fingers, not including the thumb. So this is how you can visualize the right hand grip rule. So now we have the combined electromagnetic law, which states that the combined electromagnetic law states that the EMF induced in a circuit is directly proportional to the rate at which the magnetic fixed lines are cut per unit time, and the direction of current which will be produced will be such that it opposes the change producing it, and that combined electromagnetic law is given as EMF is equal to negative dphi all over dt. Now there are different formulae for the different self-inductions of materials. Now, first case, you have the EMF produced by a rotating lamina. So if you have a rotating lamina here, and this is the angle theta, this rotating lamina here is going to have a magnetic, since it's going to rotate every time, the phi here, magnetic flux is going to be BA cos theta. The theta here is this angle here. It's produced, the theta is the, visualize that anytime we are speaking about the magnetic flux, when we are speaking about the magnetic flux, the angle theta is always the angle with respect to the perpendicular. So the angle theta, when we are speaking about the magnetic flux, is always the angle with respect to the perpendicular and not the angle parallel to the surface area in which the surface area of which we are speaking about. So here you're going to have phi is equals to BA cos theta, and this theta is the angle the B field does with the perpendicular to the area. Now the area here is going to be L times D. So phi is going to be BL D cos theta. So now let's differentiate. When we are going to differentiate here, we are going to place now the value of phi inside. So when we place the value of phi, we realize that only theta is going to be varying with respect to time. So the EMF induced is going to be BLD D cos theta. So we are going to differentiating the function. We are going to differentiate the interior and then differentiate the exterior. So now when we differentiate the interior, we are going to have d theta, and when we differentiate the exterior, so we first differentiate the interior here. When we differentiate the interior, we are going to have d theta all over dt, which is equals to omega, and differentiate the exterior is going to give you negative sine theta. So in all, we are going to have BLD omega sine theta. So it's not supposed to be this one. So the EMF of the rotating lamina is going to be BLD omega sine theta. Now let's visualize the EMF produced by a rotating coil. with an n number of, if provided that the rotating coil have n number of turns. If it has n number of turns, we are going to have A of the rotating coil is equals to NBA omega sine theta. So now let's visualize the EMF of a linearly moving lamina. The EMF of a linearly moving lamina, let's visualize in this case. Let's say in this case, you're going to have a magnetic field which is moving out of the screen. So this X shows that the magnetic field is moving out of the screen. And you have here a velocity V moving in this direction. So now in this case, you know that the EMF will be equal to the D of the phi. Now, but phi in this case is going to be BA cos theta. Now the question we have to put in our mind is that what is theta? Theta is the angle that the B field does with the perpendicular to the area. The B field here is perpendicular to the area, and the angle the perpendicular to the area, the angle between the B field and the perpendicular to this area is going to be 0 degree. So here the cos of 0 is going to give you 1. So the phi here is going to be BA. So now substituting in this equation, you're going to have EMF is equal to D of BA, where B is a magnetic field strength and A is the area. So now this area will be equal to the length here times this X here. So we are going to put A here is equal to L times X. When we substitute, we realize that this L is constant, but this X is changing due to the change in the velocity, here. So we are going to have BL D of X all over dt. So but V is equal to dx all over dt. So velocity is equal to the change in the distance divided by time. So we realize that when we substitute in this equation, we're going to say that EMF is going to be equal to the magnetic field strength times the length times the velocity. Now let's visualize the EMF induced in a rotating disc. In this case, we have a rotating disc here. As such here, the magnetic field strength is going to be in this direction here. Here you have a small rod with a certain diameter D here, and this is going to be your disc here with a large diameter big D. So we still have EMF equals to the change in magnetic flux linkage with respect to time. Now we realize that what the B field is perpendicular to the area, so the angle that's going to be produced is going to be 0 degrees, because the angle is taken with respect to the perpendicular of the area. So the angle between the B field and the perpendicular to this area is going to be 0 degrees. So we are going to say here that the EMF is equal to the D of BA all over dt. Now both the magnetic flux and this area of the disc are going to be constant. They are not changing with time. So we are going to have D into 1 all over dt here. But 1 all over t is going to be the frequency. So the EMF is going to be equal to BAF. Now this area of the disc is going to be this large area minus the small area of the rod here. So we are going to have the area of this disc minus area of the rod. But the area of the disc is equal to pi big diameter squared all over 4, and area of the rod is going to be equal to pi small diameter d squared all over 4. When you subtract, you're going to have A is equal to pi into d squared minus small d squared all divided by 4. Substituting back in this equation, you're going to say that the EMF is equal to B into pi d squared minus d squared all over 4 times the frequency. So this is your final formula for the EMF that's going to be induced in this small system here. So now let's visualize what is self-induction. And we said that self-induction refers to the ability of the material to induce itself an EMF once it cuts through the magnetic field lines per unit time. So this is what is said to be self-induction. self-induction, and we have already visualized some aspects of self-induction here. But in this later part of self-induction, we're going to realize we are going to see two main sacred elements, the inductor and the solenoid. So now we need to know that another formula for magnetic flux linkage, this the magnetic flux linkage. Another formula for magnetic flux linkage given in circuit as the inductance times the current. So the magnetic flux linkage is also given as the inductance times the current for inductors. Magnetic flux linkage equals to inductance times the current inside the circuit. Now the magnetic flux linkage is equal to the number of turns times the magnetic flux, as you have seen in magnetic field. So since we have already seen from Faraday's law that the EMF is equal to the change in the magnetic flux linkage with respect to time, which is N d phi all over dt. Now we say that since N phi is equal to Li, we are going to substitute. We realize that L is a constant, so the EMF is also equal to the inductance, the change in current with respect to time. So this is the EMF that is going to be produced. Now the question here is this formula. What is the significance of this formula here? The significance of this formula is the main basis of the function of inductors in circuits. What are functions of inductors in circuits? Inductors are used to oppose the rate of change of current per unit time. So what do you realize? You realize from this formula that an EMF is going to be produced when current is going to be changing per unit time. So this EMF is going to be produced by the inductor such that there is an opposition of current change. And this EMF is going to be negative. So the negative sign is not in place here, but this EMF is going to be negative such that it's going to reduce or prevent the change of current per unit time. So now let's visualize this diagram here. In this diagram, we have current and we have time. You know that at the start of a circuit, when you put on a switch, the resistor is going to have all the current flowing through it. All the current is going to directly rise into it to attain the maximal current when the current passes into a resistor circuit. But in an inductor circuit, we said that the function of inductor is to prevent the rate of change of current per unit time. So what's going to happen is that the change of current in an inductor circuit is going to be minute. So you are going to have a minute change of current before it attains the maximal current in the circuit. So now let's come back and visualize the energy of an inductor. So now we are going to calculate energy from the classical mechanical formula for power. Power is given as the rate of change of energy per unit time. So it implies that the dE is equal to P dt. So now, but we know that P, the power of the circuit, is equal to IV. But this V is said to be the EMF induced in the inductor, because here we want to find the energy of the inductor. So this V here will be the EMF of the inductor. So this power is equal to the EMF times the current. So when you substitute here, you're going to have dE is equal to EMF times current dt. But we also note that the EMF is equal to L di all over dt. So this is the formula for EMF. EMF is equal to L di all over dt. So now when substituting it, we are going to have L di all over dt times dt. So this dt and dt are going to cancel. So we are going to say dE is equal to Li di. So we can now start integrating. We should note that at the start, the E stored by the energy of the inductor will be equal to 0. and the current in the circuit will be equal to 0. So in this case, in this circuit here, the current at start is 0 and the energy is 0. So now at time t, the energy stored will be equal to E and the current will be equal to I. So we are going to have an integral where the lower limit is going to be 0 and the upper limit on this side is going to be E. While here the lower limit is going to be 0 and the upper limit is going to be I. So when we integrate this side, we're going to have E here from lower limit E to 0, and this integration of upper orders is going to give half Li squared from lower limit 0 to I. So the energy of the inductor will be equal to half Li squared. Now let's visualize the solenoid. The solenoid is a form of an inductor, but now we need to know that with the solenoid has a certain magnetic field. The magnetic field of the solenoid is given as mu0 Ni all over L, where L is the length of the solenoid. So now, in order for you to find the inductance of a solenoid, Li, we need to know that Li is equal to the field, and this field here is a magnetic flux linkage. And magnetic flux linkage is equal to the number of turns times the magnetic flux, which is the big field. Now this field here is equal to NBA. So when we substitute here in this equation, we're going to say the solenoid, since we know that, so this field here is equal to NBA. Now the B of the solenoid, the magnetic field strength produced by the solenoid is equal to mu0 Ni. So when we substitute in this formula and this formula, we're going to have Li is equal to Na mu0 Ni all over L. So the inductance of the solenoid will be equal to, I'll divide here by I, which is the current, so I'll cancel. It's going to give you the inductance. Inductance equals to mu0 N, which is number of turns of the solenoid squared, A, which is the area of the solenoid, divided by L. So this is the formula for the inductance of a solenoid. Now the energy stored inside the solenoid will be only equal to the initial energy we had. We've originally found that the energy of the inductor was equal to half Li squared, and now we have already calculated to the formula for the inductance of a solenoid. So it implies that the energy of a solenoid, which is an inductor, will be equal to half Li squared. We just substitute the inductance that we have found initially here. When we substitute, we are going to have mu0 N squared A all over 2L, because of this half here, I squared. So this is the first case. And now we need to note again that this is the formula of the energy stored inside the solenoid. But the B of the solenoid is equal to mu0 Ni all over L. So if I don't want to place the formula with respect to the current, but with respect to the magnetic field of the solenoid, so it's going to, I'll use B of the solenoid equals to mu0 Ni all over L. Now this I here, I can make it a factor. I will be equal to BL all over mu0 N. So when I do it, I have I can substitute back I in this equation here. When I substitute back I in this equation, I'm going to have E, which is energy of the solenoid, equals to mu0 N squared A all over 2L into BL all over mu0 N all squared. So when I do this, I'm going to have the final formula for energy stored inside a solenoid to be E equals to B squared all over 2 mu0 A L. Now area times length, the area, this A is going to be the area, the cross-sectional area of the solenoid, and this area is going to be the length of the solenoid. Now area, cross-sectional area times length, is going to be giving you the volume. So this energy is equal to B squared, magnetic flux of the solenoid squared, divided by 2 mu0 times V, which is V equals to the volume. Now let's find the energy of electromagnetic waves. From this formula above, we have found the energy of the magnetic field. And now we need to know that electromagnetic wave have two components. It has energy that is going to be produced from the electric field component, and we have energy that is going to be produced from the magnetic field component. The energy that is going to be produced from the magnetic field component has already been shown here to be equal to B squared all over 2 mu 0 V, where B is going to be the magnetic field strength of the electromagnetic wave. We can still use this formula to be the magnetic energy of the electromagnetic wave, but in this formula here, we know that electromagnetic waves do not have an inductance and do not have a current. So we instead preferably use this formula here, because the electromagnetic wave has the magnetic field strength and the permittivity of free space is known with the volume of with the volume in which the electromagnetic wave move. Now, the electric field energy of the electromagnetic wave can be found from E is equals to half CV squared that we have found inside the chapter of capacitors. So now we know that C is given as epsilon 0 A all over D. So when we substitute it, so we have epsilon 0 A all over, so this is the value of C, and the E D here, this E is the electric field strength, and this D here, so this is E, which is electric field strength, and D here. So I can substitute the different values. So we are going to say that the energy of electromagnetic wave is of the energy of electric component of the electromagnetic wave is going to be I substitute the value of capacitor, which is epsilon 0 A all over D, and now I substitute the value of voltage, which is the electric field strength times D. When I do that, this and this are going to cancel. You are going to have half epsilon 0 E squared. E here is going to be the electric field strength all into AD, but the area times distance equals to volume. So we are going to say energy of the electric component is going to be equal to half epsilon 0 E squared V. So now the total energy of the electromagnetic wave is going to be the energy of the electric component of the electromagnetic wave plus the energy of the magnetic component of the electromagnetic wave. So we are going to say that the total energy of electromagnetic wave is going to be equal to this energy here, which is for the electric component, half epsilon 0 E squared V, plus this other energy here, which is for the magnetic component, and plus B squared all over 2 mu 0 V. So now the energy density is going to be the energy per unit volume. So the energy density sigma is going to be this energy all divided by V. So the energy density of electromagnetic wave is given as half epsilon 0 E, the electric field strength squared, plus B squared all over 2 mu 0. So now we have visualized the energy of electromagnetic wave. So we can now go to the next section, which is mutual induction. Mutual induction refers to induction of another circuit, the induction of another material once this material cuts through the magnetic field, the ability of one material to induce another material with an EMF once the latter material cut through the magnetic field strength, we cut through the magnetic field lines produced by the former. So this is what is mutual induction. So this is illustrated from this diagram. So in this circuit is the circuit which produces the magnetic field lines, and this is the latter circuit that is going to be the one which is going to be induced with current. So now the circuit here consists of an alternating current and not a direct current. The alternating current is going to be changing direction every time. Since it changes direction, it's going to, at one instant, it's going to produce a north pole here. The current via the right hand grip rule is going to produce a north pole here and a south pole here. So this north pole is going to cause the magnetic field line to be aligned in this direction, and it's also going to cause the current to be induced in this latter circuit, such that the north pole should be found here and the south pole should be found here. afterward, the AC is going to align the current in this direction. So the current will be here and is going to be moving downward here. So this is going to produce now a north pole here and a south pole here. When a south pole is going to be produced here, it's going to cause this other circuit to produce a correspond to change the direction of current here, such that it should be south pole here and north pole here via the right hand grip rule. So this is how mutual induction occurs. You have an AC circuit here with a solenoid here, which is going to produce magnetic flux line that is going to change per unit time due to the change in direction of current here. And this change in the magnetic flux line is going to induce this other circuit with an EMF and a corresponding current via the Faraday's law. So we see that Faraday's law occurs because of the change in the magnetic field line due to the AC circuit here, the AC source. And also the current direction is going to be such that it will oppose you see that the north pole here is found with this north pole here, and if we realize that the current direction will be upward here, such that it will oppose the change producing it here. So this is how to visualize this mutual induction. So now transformers are circuit elements which are capable of stepping up or stepping down voltages. So now let's visualize the formulas involved with transformers. Transformers have typically the same mode of action as mutual induction. Now transformers consist of a primary circuit and a secondary circuit. The primary consists of primary circuit and secondary circuit. The primary circuit is going to cause an induction of voltage into the secondary circuit. So now the primary circuit, you need to know that the formula for the primary circuit is given as N small p phi p is equals to L, the inductance of the primary circuit, the current of the primary circuit, and N of the secondary circuit, phi of secondary circuit is equals to LS IS. So now the epsilon p, so the magnetic the current, the voltage or the EMF induced on the primary circuit will be equals to the change. If there is an EMF induced on the primary circuit, it will be equals to N of the P, the change of the magnetic flux linkage. So it's going to be the number of turns of the primary circuit times the change in the magnetic flux with respect to time, and this is equals to the inductance of the primary circuit, di all over dt. This is similar with the secondary circuit. So it implies that we're going to have LP being this and LS being this. So all these are the formulae which are involved with the primary circuit and the secondary circuit. You need to know again that the power of the primary circuit is going to be equal to the I primary circuit, the current in the primary circuit, voltage in the primary circuit, and the power in the secondary circuit is going to be the current in the secondary circuit, voltage in the secondary circuit. Using the equation above, the different equation above, we are going to have this formula here. So now we know that the flux linkage in the circuit, we have this. Now the efficiency of the transformer is going to be given as the power outputted all over the power inputted times 100%. So the power output is going to be the power input times the efficiency divided by 100%. Now the power input in the circuit here is the power of the primary circuit, and the power output is going to be the power of the secondary circuit. Now this efficiency N here is not always, is never 100%. So at times, most of the times, in order for you to make sure that the efficiency strive to attain 100%, there are certain corrections that are given below. The number one correction that must be made sure such that the efficiency to attain 100% is that there is the resistance of the winding. Some energy is dissipated as a heat due to the resistance of winding, and this heat is going to be I squared R, as you have seen in Joule effect. This is reduced due to thick copper wires. So the thick copper wires are going to be used when you want to coil at the level of the transformers, in order for you to reduce the resistance of the resistance to current. The second case, which is going to reduce the efficiency of the transformer, is the eddy current. The alternating magnetic flux induces the eddy current in the iron core. So this alternating magnetic flux is going to induce the eddy current iron core and causes heating, and therefore reduces the amount of power outputted into the secondary circuit. This effect is reduced via a laminated iron core. So you realize that every time that you have you are going to have your transformers, there will be a certain form of plastic above the iron core. This is in order for you to reduce the eddy current, because the eddy current is going to be produced. Not we initially note that via the Lenz's law. Explains that the change in the magnetic flux is going to produce a lateral EMF that's going to cause the movement of current in order to oppose the change producing it. Now the iron core, which is used in the connection of this magnetic flux, is also going to produce a current in it, and that current is going to be the eddy current, and this eddy current try to oppose the primary circuit magnetic flux. And in order to prevent this primary circuit magnetic flux opposition, we use a laminated iron core. We laminate it, or we put a plastic just on the iron core. The third point, which is going to reduce the efficiency, is hysteresis. The core is repeatedly magnetized and demagnetized by alternating magnetic field. During this process, energy is spent in overcoming so this core can be magnetized and demagnetized. So the energy can be used in overcoming the internal magnetic friction of the core. So in order to prevent this hysteresis, this continuous magnetization and demagnetization of the core, to minimize the power loss from this continuous magnetization and demagnetization, we use a core which is made up of permalloy metal. And lastly, we have flux leakage. The flux due to the primary circuit may not all link to the secondary circuit. So to minimize it, we use coil around a soft iron core. So we coil around a soft iron core. So to prevent, because at certain times all the magnetic field lines may not penetrate from the primary to the secondary circuit. So in order to minimize this flux leakage, we are going to use coil around a soft iron core. So all of these are going to make sure that the efficiency becomes 100%. And if the efficiency becomes 100%, then IPVP is equals to the power input is going to be equals to the power output. If the power input is going to be equals to power output, then it implies that the VP all over VS will be equals to IS all over IP. Now, here we need to know that the EMF induced on the primary circuit is going to be equal to the mutual inductance dI of the secondary circuit all over dt. So we see that the EMF on the primary circuit is a mutual inductance here, dI of the secondary circuit, and the EMF of the secondary circuit is the mutual inductance dI of the primary circuit. Unlike in the first case we had here. In the first case we said that EMF of the primary circuit is the inductance of that primary circuit, dI of the current of the primary circuit all over dt, and the EMF of the secondary circuit is the inductance of the secondary circuit, dI of the secondary circuit all over dt. Now the difference with this other one here is that when we use the value of mutual inductance, we use the current of the secondary circuit when you want to find the EMF for the primary circuit. And when you want to find the EMF of the secondary circuit and use mutual inductance, we use the current of the primary circuit, unlike when you have the inductance here. So this is a small difference between inductance being used here and mutual inductance being used as a constant here. So now, after having the formula above, we see that EMF of secondary circuit is going to be equal to mutual inductance dIP all over dt. So this is the formula here. So now EMF, we say that the mutual inductance now is going to be equal to EMF of the secondary circuit all over dIP all over dt. So now let's come back again here. But EMF of the secondary circuit, we also know that the EMF of the secondary circuit is also going to be equal to the LS, the mutual inductance of S, di of the secondary. Here it was EMF of the secondary equals to mutual inductance times the d of I of the primary circuit, but here is the EMF of S is equals to the inductance of the secondary circuit, d of the current of the secondary circuit and not primary circuit, dt. So when we substitute here, we're going to have this mutual inductance equals to LS dis all over dt divided by di all over dp. Now, if I multiply inside here by LP and outside, I'm going to have, there is no change. So you have LP here, dIP all over dt and 1 all over LP here. So now we know that the EMF of P is equal to LP, the dIP all over dt. So we have EMF of P is equal to dIT of P. So we see that inside here is going to be the EMF of P. So we substitute here the value of EMF of P. So we're going to have M mutual inductance is going to be equal to LS dis all over dt all over 1 dis. So now we have the value of the mutual inductance. We need to know again that another formula for mutual inductance. So the formula of, there are two formulae for mutual inductance. Mutual inductance can also be equal to the EMF of P divided by dis all over dt. So when we have this, we substitute, we are going to have this. So mutual inductance again is going to be equal to LP LS 1 all over mutual inductance. So when we multiply, we are going to have mutual inductance square is going to LP LS. So M here is going to be the square root of LP times LS. So this is the value when you want to find for the mutual inductance. So mutual inductance, it will be equal to the square root of the inductance of the primary circuit times the inductance of the secondary circuit. So now we need to note certain point. For this formula to be used, then this should be the flux leakage should be 0. It should be magnetically connected. The two circuits should be magnetically connected. That is, all the for this formula of mutual inductance to be used, the two circuits should be magnetically connected. That is, all the magnetic flux must pass from the primary circuit into the secondary circuit, and none should be lost via flux leakage. So from here we have visualized all the different sections involved in electromagnetism, and we'll say thanks for your kind attention. Please don't forget to like and subscribe for Science Video Makers. Thank you.